let's go a little more detailed into the operation of photoconductive devices. As we've seen, if the length of a photoconductor is L, the transit time, say for electrons, is L by V, and V is nothing but mu into E, and if the applied voltage is V, then E is equal to V by L, and therefore we get the relation that the transit time is L squared over mu V. We can see that the transit time is directly proportional to the length of the sample squared. So if you can reduce L, the speed will improve. Important material property is mu. If you have a material with high mobility, then the speed will be high. And of course, the applied voltage V is something that we can vary. As I showed last time, the gain is typically tau by the transit time. So at low values of applied voltage, okay, TR will be relatively high, okay, and this ratio then will not be will be less than or at best equal to 1, and as a result, if we plot gain as a function of, say, applied voltage, okay, we find, say, this is at the beginning it will be less than 1. Then at intermediate values of V, TR will be reduced, the lifetime remaining the same, and if this is reduced, the gain will increase, and then at very high values of V, TR is no doubt small, but when the electrons are swept away very fast, we have increased injection of electrons, and as a result what we have is a condition called space charge limited currents. When high injection of electrons takes place from one electrode and injection of holes takes place from the other electrode, and as a result the gain reduces to 1. So there is an intermediate range of voltage at which photoconductor shows maximum gain. What about the speed? The speed is obviously dependent upon the lifetime tau, tau n or tau p, whichever is larger, because if you, in a photoconductor, if you do a simple experiment, if you have a sample with chopped light, which comes in bursts, okay, and then if the light comes in pulses like that, the photoconductive response time is determined by e to the power T by tau type of relation. So the response time is determined by this the minority carrier lifetime, and obviously if this minority carrier lifetime is small, then you have high speed, but the gain is small, as we've seen. So the cutoff frequency can be shown from an analysis of the AC response, which I'm not going into. The AC response is given by, suppose you have a modulated current at a angular frequency omega, then I omega squared will be given by omega squared tau squared over 1 plus omega squared tau squared, and from this you see that the cutoff frequency is nothing but 1 by 2 pi tau. We've seen that the gain is tau by t, tr. So the gain bandwidth product Fc into G is 1 by 2 pi tau into tau by tr. Tau's cancel. So 1 by tr, and tr was calculated earlier, so this is just mu v by L squared. Okay. This is an important consideration, that the gain bandwidth product of a photoconductor is determined by mobility. The lifetime does not come in here. You can get higher gain by having higher lifetime, but then the speed is slower. Okay, so the gain bandwidth product depends upon mu, and of course you can play around with, you can get high value by reducing L on increasing V, until of course there's a limit. At high V, not only do you get space charge limited current, at still high voltages you will get breakdown. Okay, so there's a limit to V then. Okay, noise in photoconductors. I want to take this up as a simple example because I've emphasized that noise is important in all photodetectors. As I've said before, that here we have in a photoconductor we have, obviously it's a resistor, so we have Johnson noise. The Johnson noise current squared is given by 4 kb T into bandwidth divided by the photo RC, and we have a generation recombination noise which is given by 4q gamma, which is the gain I0b over 1 plus omega squared t squared. So the signal to noise ratio, the signal has fluctuations in photocurrent Iph squared, and the noise has these two contributions, Ij squared plus Igr squared. So based on this, one can draw an equivalent circuit. Iph, then you have the generation recombination source. Conductance GC is just equal to 1 by RC. You can write this as 4 kBT B into GC. And the Johnson noise source IJ squared bar. Okay. So this is the typical noise equivalent circuit of a photodetector, photoconductive detector. Now, if you consider that here's the photoconductor and we have light incident on this, let the incident light power be given by P omega is equal to P opt. It has a DC component plus a modulated component, M. This is the index of modulation. It can vary from 0 to 1, and this is the AC frequency. P opt is the average optical signal power. Then from this equivalent circuit there's a DC component of current and there is a AC component. The AC current component at omega frequency, this is RMS, is given by Q eta P opt M. The root mean square is given by 1 by root 2. The number of photons, if you have power P opt, photon energy h nu, so this gives the number of photons, okay, P opt by h nu, and this is the gain term. And that gives the frequency response. So we've already we want to calculate the signal to noise ratio. So we know what IJ squared is. We know what IGR squared is from this. We know what IP is. Okay, IP or IPH. And if we put them all together, we get the signal to noise ratio is eta M squared P opt by h nu. That's just the number of photons incident. And you have this 4 kT GB, this giving you 4B. So we see that the signal to noise ratio obviously increases as the index increases. It increases as it depends upon the quantum efficiency. Okay, if you have a high bandwidth, okay, the noise is large and the signal to noise ratio goes down. And if you look at this expression, okay, this is actually in the denominator of 1 plus kT by Q TR by tau 1 plus omega squared tau squared G by. Okay, so you can see that there's a frequency dependence given by this omega squared, and if you increase terms in the denominator, then the signal to noise ratio goes down, and if you decrease these values, then obviously the signal to noise ratio goes up. So there's temperature here in the denominator also. Okay, so as temperature goes up, obviously the noise it's a general phenomenon. You have Kp, B here, this torque. So if T goes up, the signal to noise ratio will go down. So this is a typical example of how you can calculate the signal to noise ratio. Okay, this is of a simple device like a photoconductor, in which there are two sources of noise. This generation recombination as well as the Johnson noise. Now I won't go through such calculations for all the devices, but I can say that obviously for photovoltaic detectors, okay, in addition to these sources of noise, you will have shot noise. Okay, so you can make an equivalent circuit which includes shot noise. For APDs, it's a special type of photo. You will have, in addition, you will have the avalanche multiplication noise. And from the point of view of detecting weak signals, it's always our endeavor to try and maximize the signal to noise ratio by either increasing M or reducing temperature, reducing bandwidth, and some of the material parameters involved also.
And is the binomial expansor or 1 by unit? SY and SU?
Yeah, this should be in the denominator, okay, to the power minus 1. So this whole thing should be in the denominator. Okay, and this brings me to the next type of detectors, which are photovoltaic detectors. Broadly, they consist of, they can be either PN junctions, special cases PIN, APDs, avalanche photodiodes. They can also be metal semiconductor junctions. If you consider broadly their properties, spectral response it is almost like photo conductive detectors, because after all, in this case you have a PN junction. The spectral response depends upon light coming and exciting electron hole pairs. So again, the relation is that H nu must be equal to or greater than Eg. And Eg can vary, say for example, for wide band gap semiconductors such as cadmium sulfide, Eg will be of the order of 2.4 eV, silicon 1.1 eV, germanium 0.67, and important detectors are things like indium antimonide, mercury cadmium telluride, about 0.12 eV. So these are important IR photovoltaic detectors. A special class of photovoltaic detectors are solar cells. I won't discuss them. Large area photovoltaic detectors, typically and they match the solar spectrum which peaks around about lambda, about 0.5 microns. And as you know, for PN junction devices, you have a built-in field. So one major difference between photoconductive and photovoltaic devices is that you don't need a bias. You don't need an electric field. For solar cells, obviously, you are generating electric energy from optical energy. So the built-in field is separating the electron-hole pairs. But let me mention that in the case of photodetectors which are used in the infrared, often you do use a reverse bias. Often, in order to get higher speed, in APDs, obviously there is a high voltage applied. Often you do use a reverse bias in order to get a higher speed of response. But whereas a photoconductor, absolutely, it is absolutely essential to have a bias. In this case, you need not have a bias because the junction itself separates the charge carriers. Okay, and as you know, for a PN junction, you have a relation I is equal to I0 e to the power QV over NKT minus 1. Okay, and from this you can optimize the performance of a solar cell to get maximum efficiency. I won't go into details of optimizing properties of a solar cell, except to say that a solar cell is tuned to the solar spectrum available at the Earth's surface. It's basically broadband, centering around 0.5 microns. It extends way beyond the infrared, and as a result, the overall efficiencies available for solar cells, maximum theoretical efficiency is only about 30-35%, because it is very wide spectrum and you cannot optimize the solar cell. You cannot match the band gap to a particular energy. However, the difference between this and typical photodetectors is that photodetectors are by their very nature used in optical systems in which you have narrow wavelength region. For the case of a laser, it's a very sharp, specific few angstroms of spectral width. So you can match Eg to h nu, and you can get internal quantum efficiencies going to 1 and external quantum efficiencies could be something like 90% or more, because these are narrow wavelength devices. Right. One of the very special types of photodetectors are PIN photodetectors. They have the advantage of relatively high speed, and we want to have high quantum efficiency or responsivity. And the reason one has this eye region is that by varying the width of the, if you have light incident from this side, then obviously the light is going to be absorbed in the semiconductor as, suppose you have P incident intensity, this is P incident e to the power minus alpha x. So one can adjust this eye region width, which can be a few microns, in order to absorb most of the light. If this eye region was not there, then quite a bit of the light would not be absorbed, and as a result the quantum efficiency and the responsivity would be low. The number of electrons created per photon would be low. Another advantage of this eye region is that when this is reverse biased, there is a high field across this eye region. If I draw the band diagram of a PIN diode, suppose as I've drawn it here, we have, okay, let me draw it again. Suppose the eye region width is W. WP, WN. We have P opt coming in, and for any material there will be a certain amount of reflected light, R P opt. We want to have depletion layer conditions, so this eye region should be depleted of carriers, so that any carriers created by the light should be detected and separated very fast. So we have reverse bias, N positive, P negative, and as a result the band diagram will be something like this. Okay, so this is the N-type region, this is the P-type region, this is the Fermi level here, that's the Fermi. So this is the applied bias, QBR. Okay. This is EC, EV, and when light is incident, if electron hole pairs are created here, if they are created within this diffusion distance, then they will diffuse and the electrons will move, and the holes will obviously be, this is negative okay, and this is positive. So the holes will migrate towards the negative electrode, electrons towards the positive electrode. This is a small region, few thousand angstroms. This is again a small region, so quite a lot of the light will enter into the I region where electron hole pairs are created, and here this is the main absorbing region where electrons and holes are separated due to this built-in electric field. And due to this negative bias, this is a depleted region. Okay, so this is a region where there is a drift field present. Pardon? No, it is not an insulator. It is relatively lightly doped. I stands for intrinsic, right? But it need not be absolutely intrinsic. It is relatively lightly doped. The Fermi level should be somewhere near the middle of the band gap. Okay, so and this sustains the electric field applied, which is mainly if this is P and this is N, as you can see, this is a relatively high resistivity layer. So the voltage applied appears across this high resistive I layer. Okay. In silicon, for example, if you have a silicon p-ion diode, you can get intrinsic. Okay, you can make it intrinsic device. But suppose if you take a InGas, indium gallium arsenide, which is used in infrared, it is difficult to get an exactly intrinsic material, but it can be high resistivity. Okay, the carrier concentrations here, if they are 10 to the power 17, 18, here the carrier concentrations will be 10 to the power 14. Okay, this is the electric field profile. And what about the optical intensity variation? If you have P opt over here, you have P opt into 1 minus R, right, at the, and this decreases with distance, okay, as P opt 1 minus R into e to the power minus alpha x, where alpha, remember, is a function of wavelength. Okay, so alpha at a particular wavelength, and one can say that, okay, at some point x here, which is at x equal to 1 over alpha, the intensity decays to 1 by e of its value. Okay, so this width of this I layer is chosen taking into account the value of alpha. Okay, if alpha is 10 to the power, say 2, then this is 1 by 10 to the power 2, so that may be a few hundred microns. But if alpha is 10 to the power 4, then 1 by alpha is of the order of microns. So for example, in silicon, the I layer could be something like 20 to 20 microns. Okay, for InGas, the so-called I layer could be something of the order of 2 microns, okay, depending upon this optical absorption coefficient at that particular wavelength. Okay, now obviously when light is incident, electron hole pairs are created, and the electrons drift to the n side. This becomes negative, this is positive. What are the contributions to this current? Firstly, of course, there is the electron hole pairs created in the I region, which is separated. Okay. Then there are electron hole pairs created in the P region, where this electrons diffuse, okay, towards the junction, and here a little bit of light also gets into the N region here. So suppose electron and hole pairs are created. Okay, there is no field here, so it is the difference is here there is an electric field separating the carriers. Here the motion must be by diffusion. So there will be a small current due to hole diffusion. Okay, so these are the components of current in the PN junction, and one can analyze them. So what is the total current? The total current density is drift plus diffusion. This is the current outside the drift region. And this is due to the current in the I region. And these carriers are created by light. The electron hole generation rate Gx is, say, phi 0, the intensity of the light, into alpha, the absorption coefficient. The intensity of the light at a point x is phi 0 e to the power minus alpha x into alpha. Okay? So where phi 0 is the incident photon flux per unit area, that is just P opt 1 minus R, divided by area, and number of photons is just h nu. Okay? R is the reflection coefficient, A is the area, h. If it's monochromatic, it's h nu. So what is the drift current? That is the current due to this generation Gx dx, which takes place within the width of the drift region. I should take the coordinates here. This is 0 and this is W. Okay, and this is just Q phi 0 1 minus alpha W. So that is this term. What about the diffusion term? Say for x greater than W, minority carriers, these are in the n-type region, these are holes, diffuse towards I region. The motion is governed by one-dimensional diffusion equation, which is dp delta 2 pn over delta x squared minus pn minus pn0 over tau p plus gx is equal to 0, where pn0 is the equilibrium hole density. What is the boundary condition? Here we are talking about holes in this region diffusing towards the junction. So the boundary condition is that x equal to infinity, Pn is just equal to Pn0, because there is no light, penetrating light towards the junction, towards the end of the device, and at x equal to W, Pn is equal to 0, because the holes then diffuse into the I region. So if you solve this one-dimensional equation with these boundary conditions, the solution is Pn is equal to Pn0 minus Pn0 plus C1 e to the power minus alpha W into e to the power W minus X by Ln, where Ln is the diffusion length, plus C1 e to the power minus alpha X we are talking about holes in the N-type region, right? So this should be LP, should it not? Diffusion length of holes in the, which is given by this, and the constant C1 is just phi 0 by dP alpha LP squared over 1 minus alpha squared LP squared. So this is solution for Pn. We want to calculate what is the diffusion current. So what is the diffusion current? J diffusion is just minus QdP into the concentration gradient. That's delta Pn delta X at X equal to W. Okay. So we know this, and all we have to do is take dP and dx. Okay, there's an X variation here, there's an X variation there. So if you calculate that, then you get C1 term gives you this one, Q phi 0 alpha LP over 1 plus alpha LP e to the power minus alpha W from this term, and then there is QPN0 dP. If you substitute for Pn here and work this out, then you will get this expression. There are two terms. So this is J diffusion. I've already calculated out J drift. So one gets the total current So this is total current of at a PIN diode due to a flux phi 0, and the width of the PIN diode is W is the I layer thickness. Okay. Alpha is the absorption coefficient at a particular wavelength. Okay. Minority carrier properties are given by dP, LP are the minority carrier properties, and Pn0 is the hole concentration in the N-type region. Now this is quite small. Pn0 is small, so this is considered negligible in most cases. So as a result, we find that under normal operating conditions, what is the quantum efficiency? This is just J tot by Q, that's the number of electrons divided by number of photons, that is P opt by A h nu per unit area. Okay. And so here is this expression when you divide by phi 0 has this P opt A h nu. So the relation is just 1 minus R. This phi 0 has that term. Phi 0 is P opt 1 minus R E h nu. Okay. So we divide by that, so we just get 1 minus R into this term. 1 minus. This is a relatively simple expression, and this gives the quantum efficiency of a p-ion diode. This is just a reflection term. Okay. If you by suitable coating, you can reduce this, and notice that for high eta, what do we want? We want alpha W to be much greater than 1. Okay. What does that mean? That W should be much greater than 1 by alpha. In other words, this just means that all the light should be absorbed. The width of the eye region should be such that it should be much larger than the absorption depth. Okay. Of course, we want R also tending to 0. And if you look at the denominator, we want alpha to be large, and alpha LP should be relatively large. Okay, so that this term, this minus term, if alpha LP is large, then this minus term is also small. Okay. But remember, this term is not so important as this term because this is in the exponential. So this is the general quantum efficiency of a p-ion diode. Next time what I'll discuss is that, okay, how do we obtain this condition? Because if we have W much larger than 1 by alpha, the transit time of the electrons will be quite large. Okay, so if W is large, then we have high efficiency but relatively low speed, and if W is small, we have relatively low efficiency but the transit time is small, so high speed. So this means there is a trade-off between speed and efficiency, which I will discuss next time.